Thanks, Brian. I'd like to start this presentation by first explaining what we'll be building in this webinar series. So the goal of the webinar is to provide an introductory example of image classification applied to robotics. So what does this mean? So we'll start with what is essentially the hello world of ROS2, if you've ever been exposed to the robot operating system. So they have this robot simulation called TurtleSim, which is a very simple two-dimensional simulation, but it still exposes all the concepts that will be applied in robotics. So it consists of two nodes. One node takes input from the keyboard and generates three-dimensional velocity commands, which specify translation and rotation in X, Y, and Z directions, and then controls this two-dimensional simulation of the turtle robot. So what we're going to do is take this example, remove the keyboard input, and replace that with the camera input. Then we'll analyze the image from the camera input to identify hand signs, which is our image classification, and the subject of this first webinar. Then, in the next webinar, we'll be taking these detected hand signs and converting them to velocity commands, and of course showing how all this integrates into the robot operating system. So to control our TurtleSim robot, we'll use A for advance, B for backing up, L for turning left, and R for turning right. Our robotics applications will be accelerated and deployed on the ZU board. First, using AMD's Vitis AI to accelerate the image classification model, and finally integrated into a ROS2 graph to create our final robotics application. For the sake of time, this will be done with the pre-built SD card image shown in the link here. If you want to understand how this SD card image was created, please follow the series of 4 Hackster projects illustrated in this slide. The content for this webinar has been provided as Jupyter notebooks, which will be executed on various platforms. To start off, we'll take a look at our data set. Then we'll define our model and check for compatibility with the Vitis AI tools. Next, we will train our model, then deploy it to the DPU using Vitis AI, and finally, we'll execute it on the ZU board. For our first notebook, we need to first get started with Kaggle. So Kaggle is an online service that has a repository of datasets as well as server instances for running machine learning algorithms on these datasets. So the first thing that we'll do is create an account on Kaggle at the link provided here. Then we'll create code, which is Kaggle's naming for a notebook, and this runs on a Kaggle kernel, which is the server instance, which may or may not have GPUs associated with them. Then we'll associate a dataset with this code, and we'll import the notebook from my repository and run it on the Kaggle servers. So the first thing to do is to create an account, which I'll do with my email. We need to agree to the privacy and terms. Specify our 6-digit code. And now we have our account. So as we can see here, this is our cockpit where we could participate in competitions for classifying that are associated with data sets. We can create models, create our code with our notebooks. We also have this little icon of ourselves, which basically displays our status. All right, so the first thing to do is look for our data set. ASL, the American Sign Language. So you can see here, 87,000 images corresponding to 29 classes. the letters A to Z, as well as 3 special characters. All right, so we want to create a new notebook with this data set. We can rename the notebook to something more meaningful. Feel free to choose the name that you want. This is personal preference. Then we want to import the notebook from the webinar content. So if I go to the Alberta Beef ASL tutorial under the 2022.2 branch, we'll take an archive of this. Extract that file. You can see here we have all our notebooks. So we'll want to import this into our Kaggle we could run our entire Jupyter notebook by pressing Run All, and we'll follow it as it executes. So first we import some Python packages. We define our system configuration. This is specific to TensorFlow. Specify whether we have a CPU or GPU. So right now we're running an instance without GPU, so that's why we get using CPU. We actually don't need to download any data because the data is already directly in the Kaggle, associated with the Kaggle kernel. The data is in this type of structure, so we have ASL alphabet and has a train subdirectory with the 29 subdirectories. Each directory is named according to the class, so either the letter or the special character. If we display one image per symbol, we can see here our hand signs of interest. So the A for advance, B for backups, open hand, L for turn left, R for turn right, and our special characters, delete space and nothing. So when there's no hand, it's important to see that there's no hand. So in terms of histogram, we just count the number of images in each directory to confirm that we have 3,000 images for each class. So we have our balanced data set. And this is an interesting one to visualize. So we can see here the data set. If we visualize it as a video, you can see that there's a lot of repetition in the background. The data set author has made the effort to have different sizes of hands, different lighting conditions, which is excellent. But in terms of the quality of the 3,000 images, we can see there's a lot of repetition. So I would question if, although there's several thousand images per each class, if they're suitable for a full-on training. For transfer learning, which is what we're going to be doing, I think this is looking like a good data set. So for use with TensorFlow 2, we're just going to define some configuration for our data set. And since the directory already has the format that we want, we could use this image dataset from directory to directly create a dataset class, which is compatible with TensorFlow. And using this dataset class, we can also just scan a variety of images just to visualize our data. So once again, we can see the background looking pretty common. We may just want to, if we get some weird behavior, we can maybe make sure that it's not training on the background and it's actually training on the hands. Something to watch out for. In our next notebook, we'll be defining our model and checking for compatibility with Vitis AI. Since this will be running in Vitis AI Docker, we first need to look at the Vitis AI tool suite. First place to start is the Vitis AI GitHub repository. And we want to look specifically at the 3.0 version. And we can see here that this GitHub repository contains most of the sources for use with Vitis AI, but the documentation is on a separate github.io page. which is very well done. So we can see that Vitis AI is part of a Vitis development environment, targeting edge, cloud devices. Here we can see the key components of Vitis AI. So we have our DPU engine, which is the IP core running in the PL that accelerates our machine learning models. We have the model ZU, which contains pre-compiled models. And for making custom model deployment, we have our model inspector, quantizer, and our compiler. And of course, for execution, we have our runtime and the library API as well. So in the documentation, the Getting Started recommends two flows. So either using the pre-built images and running the existing models and examples, which is available, the pre-built SD card image that's available for the ZU board, or to create a custom model, which is what we're doing in this webinar. So of course, all this runs on the DPU. So what is a DPU? It's an IP core that instantiates in the PL of the Zynq UltraScale Plus device. It's a matrix of processing elements. The DPU is very scalable, so depending on the number of resources available in the PL of a specific device, a different size of DPU can be instantiated. On our ZU board design, we have the B512 instance of the DPU. So the supported target platforms for Zynq UltraScale Plus, we can see here we have the ZCU102 and 104, as well as the Korea K26. And we could also add the ZU board since it's been being provided by Avnet. If we look at the host installation, we can see that there are several options to work with Vitis AI. We'll be using option 1, which is making use of the Vitis AI Docker containers. To launch this Vitis AI Docker, we'll be running this on a Ubuntu 22.04 machine. So the first thing to do is to clone the 2022.2 branch of the ASL tutorial repository that we saw previously. This time we'll do it on the command line with git clone, and we'll change directory to the ASL tutorial directory. Then I've got a script in there that will pull some files from the Vitis AI repository from AMD just to set up and launch the Docker. Then we want to pull the actual Docker from the cloud that's provided by AMD Xilinx. And this one, the one that will be used is called Vitis AI TensorFlow 2 CPU, since I do not have a GPU on my Linux machine. But if you do have one, there's also GPU versions that you can use. And then to launch the Docker, we simply launch with this Docker run script. Once the Docker is running, we want to activate the Vitis AI TensorFlow 2 workspace. So this is done with the conda activate command. Next, we want to launch the Jupyter server. So this is just done with Jupyter Notebook and specifying the IP address of your machine. In my case, this was 10.0.0.190. This will generate a token that needs to be copied and pasted to a web browser. So we copy this token to a web browser. This can be run on any machine. Here we have, once again, our Jupyter notebooks. So we're going to check the compatibility of our Vitis AI model. So the model that we've chosen to use is the VGG16, and it's been chosen for simplicity. It's got a very nice symmetrical structure. We can see it's composed of several convolutional layers, which start off as the same size as the input, with a little more depth, or have a depth of 64. And then we have a max pooling layer, which is basically a downsampling operation layer. And from there, we have another stack of convolutional layers, another max pooling for downsampling. And at each of these stages, you'll notice that the width and height diminish by a factor of 2, and the depth increases by a factor of 2. Now, these convolutional layers are often called the backbone, or the feature extractor, if you want. And the final layers are the actual classifiers that are specific to our application. So in order to verify if this model is compatible with Vitis AI. We start by creating the model in TensorFlow. So we'll be creating the original VGG16 for the ImageNet with the 1000 classes at the output using this API call, VGG16, pretty straightforward. We want to have it loaded with the ImageNet coefficients, the weights. And we can see, we instantiate our model here, and then we create our inspector class, our model inspector, and we need to specify the architecture. So in our case, it's the B512. If we look at that, the JSON file that was generated when we created our DPU design corresponds to this fingerprint. So we want to specify that as our DPU architecture when we create our model inspector class. With this, then we pass the VGG16 model to the inspect model function, and we get this long output of analysis of our entire model. So if we just scan through here, we can see that for each layer, it will determine if it can be targeted to the DPU. So starting with our input layer, we can see our first convolutional blocks, which are 2D convolutions, can be targeted to the DPU. Everything's looking good. Our max pooling as well is supported. As we hit our fully connected or dense layer, we can see that we have an issue here, where there was an error, some weights are too large to be loaded into the parameter buffer. So we'll need to analyze this. So as it is, the fully connected layer is not supported by the DPU. So as we saw in our notebook, we have an incompatibility here with our fully connected layers, including this flattened layer. If we analyze this further, looking at the DPU product guide, we can see that for the fully connected layers, our input channel needs to be smaller than 2048 times the channel parallelism. Now, the channel parallelism is specific to the DPU architecture, and for the B512, this is 8. If we plug this into the formula, we can see that our flattened layer of size 25,000 is way bigger than the limit, which should be 16,000. If we take this a little further, there's also a note saying that in convolutional neural networks, the flattened plus fully connected layers get converted to a 2D convolutional layer. And in this case, the size of the input feature map corresponds to the kernel size. And if we bring back that very long message with the very complex formula that I'll repeat here just for convenience, we have our kernel width and height times depth multiplied by our input channel parallelism divided by the weight bank width times the output channel parallelism divided by the weight bank number. And this formula resolves to 3136, which is larger than the maximum allowable of 2048. So what does this mean? So as we mentioned, we can see that our fully connected layer has been implemented as a 2D convolutional layer, and the kernel size corresponds to our 7x7 max pooling layer here. So the kernel width and height would be 7 and 7. Once again, our channel parallelism is 8. So if we plug our numbers into our formula, we can see that we have 3136 divided by our weight factors, which is larger than the 2048. So by deduction, if I understood this correctly, our weight factors are actually just 1, and we need to bring this kernel width and height smaller such that this formula will resolve to a value that's less than 2048. So for that to happen, kernel width and height has to be smaller than 32, or each of width and height need to be smaller than 5.6. Now, the way I resolve this is I added an additional pooling layer, max pooling layer after the feature extractor, which brings the flattened layer down from 25,000 to 4,608. And it turns out this makes all the formulas happy. So this would be our new modified VGG16 architecture that will be supported by Vitis AI. Now, if we rerun the model inspector on the modified model, this is where we added the additional max pooling layer to bring our flattened layer down to 4,600. And once we rerun this into the model inspector, we can see that this time, if we look at our layers that are supported by the DPU, we now have a fully connected layer that's supported by the DPU. Now, our last layer, the softmax is not supported because we don't have this enabled in our DPU engine, but that's not critical because at this point, it's the final layer and we don't need to go back and forth to the DPU. So this is actually pretty standard to have that last step being done in software for the softmax. So we now have our modified VGG model with this architecture. So this is the modification that we made. Added the max pooling layer and changed the classifier to fit our use case, which is 2029 classes to classify. All right, now that we have a model that's compatible with the Vitis AI tool suite, we can train it. And this is where we really see the benefit of Kaggle. I've gone through several iterations of this training with transfer learning, and running it as a Kaggle kernel was 10 times faster, more than 10 times faster than my local Linux machine without a GPU. So that's where all my experimentation has been done. And once I'm happy with my my training strategy, I run it one final time with the Vitis AI Docker just to make sure that it's compatible with the quantizer and compiler stages. So let's move on to this. So one option could be to train the entire model, in which case every layer in the model would be trained. Now, the advantage of this is it would probably give us the best accuracy, probably close to 99% in this case for a relatively simple use case. The disadvantages are very long duration of training, probably days. One thing that's certain is it's beyond the 12-hour limit of a single Kaggle kernel session. So it's not applicable here in our use case where we don't have a GPU. And it requires a lot of data. And we already noticed in the data set, the ESL data set, that there's a lot of repetition in the data. So like a full-on training would really need thousands of images for each class, whereas we're questioning whether there is actually several thousands worth of differential data in that data set. There's probably only many hundreds of differentiable data. So we won't be doing full-on training. Instead, we'll be doing transfer learning, which I think is a good use case for this data set as well. And if we don't have enough data, what will happen is we'll have overfitting. So the graph will probably look something like this, where we would hit an upper bound, maybe 70% of accuracy. And what causes this is the model tends to overfit the data. So it memorizes the training data and cannot generalize to the validation set. Another technique would be transfer learning. So we want to take the benefits of the model that's already been trained on a data set and apply it to our new data set. So in this case, we'd want to freeze the feature extractor, the backbone of the model, and only train the classifier. Now, the benefits of this is much shorter training cycles. The disadvantage, I've run this, turns out that we hit a plateau on the accuracies, about 90%. So it turns out that in this case, the ImageNet features are not transferable to the American Sign Language. So a solution to this is what we call fine-tuning. So in this case, we don't freeze the entire feature extractor. We keep the last layers trainable and only freeze the very first layers. So in this way, we train the last convolutional layers of our feature extractor as well as our custom classifier. It turns out this is the strategy that works really well. The benefits are, once again, much shorter training cycles. On Kaggle kernels, it's about half an hour. on my local Linux machine without the GPU, it's 6 hours. I've been achieving excellent accuracy, so 99.3%, which is phenomenal. So I've not seen any disadvantages of using this strategy. So this is the one that I'm proposing for the webinar. So if we look at our Jupyter notebook for the training, you can see that we're using the transfer learning with the fine-tuning of the last convolutional layers in our network. So as before, we are including our Python libraries, just making note of the TensorFlow versions, doing our system configuration, the data set. We'll be taking the reduced data set where we only extracted 250 random subset of the 3,000 images per class. So once again, to recap how this model is built, we start with the convolutional base. We freeze all but the 4 layers, and this is done by setting the trainable parameter of each layer to false when we want to freeze it. So we're doing this for all the layers except the last 4. And then we add our custom classification layer as well as our additional pooling layer here. So here's our additional pooling layer, flatten layer, our first dense layer of 256, and our final layer with 29 classes. Prepare our data set. So we can see that before training, our accuracy is very low, which is to be expected. These are weights that have been trained for ImageNet, so they're not yet applicable. We take a timestamp to see how long this takes, and we launch the training. So we can see within the very first epochs that we're already jumping at almost 90%, and it just keeps rising. So you can see here our training accuracy here, and then it's checked with our validation accuracy at the end. So at the end of our 51 epochs, which is half an hour of execution time, you can see here 29 minutes, we've reached 100% training accuracy, and on the data that it's never seen, 99.1% accuracy. Plot the training results. These are the same graphs that we saw in the slides. So this is a 30-minute training cycle on Kaggle. So we can see that in half that time we've already stabilized. So we could even almost say that it's 15 minutes training time on a Kaggle kernel. And one way to measure the performance of our model is the confusion matrix. So this is just a matrix indicating for the expected ground truth for all the images that have the sign A, how many were predicted correctly? Well, 50 out of 50 were corrected correctly for the A. For the B, we can see where the errors start to happen. It's on the G. Was labeled as a, I don't know what that letter is. We'd have to zoom out. Here's some, so we can see the W is getting, there's 2 instances where it was incorrectly labeled as a V. I think V and W are pretty similar symbols, and similarly the X was incorrectly labeled as R and an S. but overall these are very, very, very good results. And we can see some of the examples. So out of the 1,000 odd validation images, we can see there's 11 that were misclassified. So an M here was classified as an M, an E as an S, the delete key was incorrectly classified as a J, etc. So if we look at the letters that we're thinking of using, the A, B, L, R, delete and space, we can see here maybe our space might be seen as an O sometimes. So things to watch out for. But overall, I'm very, very happy with these training results. And we could even go look at the version that was run on the local Linux station in the Vitis Doctor. So in this case, it's the same notebook. I'm just going to scroll down to the training results. Fairly similar. In this case, we achieved the precision of 99.3, so a little better than the Kaggle, but that's just a random result. So on the Vitis AI Doctor, I had to install the Seaborn package to run the Confusion Matrix. If we look at this, we can see that the M is incorrectly classified as R. The N, there were 2 misclassifications as M. But overall, very, very, very good performance. So if we look at the wrong predictions, this time there's only 10 of them. We can see that the N was misclassified for an M, M for an R, N for an M twice. We can see here, here's a good example of the data set having very similar images. These are actually different images, but very, very, very similar. They're understandably misclassified in the same way. So in this case, an F was misclassified as the W, probably because it's having a hard time seeing the index and the thumb here, the overexposure. But overall, once again, very, very good results. Very happy with this. With our model trained, we now want to deploy it to the DPU with Vitis AI. So if we go back to the Vitis AI documentation, you can see that the flow for quantizing and compiling consists of taking the model that's output from our deep learning framework, either TensorFlow or PyTorch, quantizing this, and then compiling it to generate our microcoded instructions for a DPU engine. So if we go to the deployment notebook, we can see that we reload our model. So we load the pre-trained model. Then we want to create our Vitis quantize class, into which we'll specify our pre-trained model, and then we want to call the quantize model with our validation data set, as well as specifying 8-bit quantization. So this process takes about 5-10 minutes, and then we'll get the quantized model. We can re-verify the performance of this model. So you can see here I evaluated the performance on the training and validation accuracy. The training is still 100% accuracy, and the validation is more the one that we're concerned about, is still at 99.3% accuracy, which is very good. So we save that model. And now it's time to compile a model to create the microcoded instructions. As you can see, I'll be compiling it for many different DPU architectures. So for the ZU102 and 104, as well as our Ultra ZEV, those platforms would have the B4096. The Korea platforms would have the B3136. Ultra 96 V2 would have the B2304 or 1152, and the ZU board, the B512 and or B128. So by compiling for each of these DPU architectures, we'll have an example that can run on all these platforms. So you can see here the compilation process for each of the DPU architectures. 4096, 3136, 2304, 1152, the B512, the one that we'll be using, as well as the smaller B128. And if we take a look at where these models were generated, we have a model directory and a subdirectory for each of the DPU architectures. So for our B512, we can see that we have our ASL classifier.x model, which is our microcoded instructions that will run on a DPU, as well as a MD5 sum and some metadata that's used by the Fidus AI library API. All right, now that we have compiled our model for the Zynq UltraScale Plus device, specifically the B512 DPU, we can deploy it on our board, on the ZU board. So the hardware setup that we'll be using for this is, of course, the ZU board. We'll be programming the 2022.2 SD card image that we mentioned at the beginning of this webinar into the micro SD card. We'll have the ZU board connected to its USB-C power supply. We'll have this connected to the PC with a USB to serial port, as well as an Ethernet connection. And we'll be using MOBA Xterm to do an SSH connection and do some remote X windows to display our video. And we'll be using a USB camera for the video input. So to launch this on the board, we'll be using a pre-packaged archive with all the files that we need to run this on the board. So we'll be fetching this file with wget command directly on the board. Then we'll be extracting this archive using the tar utility, and we'll be launching the application as a Python script. So we'll launch our serial console, which is TerraTerm on Windows. Press the power button. Let's hit ZU board. This will boot Linux. We can log in as root. And we can see in the root directory we have a few files. Before adding content, we'll go to the DPU software optimize under the Zynq MP, and there's a little directory that will extend the partition to the full size of the SD card. We will look at the IP address that we've been assigned. So in my case, it's 10.0.0.178. We'll launch MOBA Xterm and create a new session. 178. And make sure in the advanced settings that we have X1 forwarding enabled. Once again, log in as root. We'll type the wget command to get our archive. Extract this archive to the root directory. Then we CD to the extract a directory. Let's just do a look at what's in our model directory. So we can see we have the X models for each of our DPU architectures. So just to make sure that we can verify which DPU we have active in our system, we could look at which apps are running, and we can see with this 0 that the benchmark app is running, and this is the one with the DPU. We can actually verify which DPU this is using xDPUtil, and we can see it's the 512. So we can launch our classify script by specifying this model. And we can see that by default, when there's no hand, it's detecting nothing, which is a good thing. We test our 4 signs that interest us. You see it's detecting the A with a few misclassifications. Doing a good job on the B. The L as well. As well as the R. Test some of those special symbols, space. Delete. Nothing. So our model's doing pretty well. I think it's ready for our next step, which is integrating this to control our turtle sim robot simulation.